to our discussion of mobile phase pH effects on acids and bases. Based on at least 3 emails, it's clear that you guys have, some of you guys have a really deep misunderstanding of acid-base chemistry. What do you think the half-life of this reaction is in water? No idea? None? How long does it take for a proton to get off of that into water in a sea of water?
Almost instantaneously.
It's almost instantaneous. That's exactly the right answer. Manfred Eichen got a Nobel Prize in the late 1950s for inventing a couple of methods for measuring very, very rapid chemical reactions. These things have rate constants that are virtually at diffusion control. On a chromatographic time scale, these reactions are absolutely instantaneous. So there's no possible way to separate HA from A-. As soon as you get a chemical separation and there's water around, the A- will react with water to go back to HA if it's not in equilibrium. And if HA is too high, it will dissociate into A- almost instantaneously. There's only one peak. Doesn't matter whether it's 90% HA and 10% A- or the other way around. There's only one peak. That's what those equations would be nonsense if there were 2 peaks. Okay? Now, if you inject an acid-base system in a buffer that's different than the eluent buffer, then you can get into trouble because the 2 buffers can screw one another up, and you can get a highly distorted peak under those circumstances. You don't want to inject an acid sample or a base sample into an eluent which has a very different pH. You want to pre-buffer that sample by diluting it with some of your eluent to get the pH adjusted properly. Okay, there's only one peak for an HA, A- pair. If you have a zwitterion, there's only one peak. If you have 10 EDTA with 6 possible protonation sites, there's only one peak. Okay? Now, if A, your analyte, injected onto the column isomerizes into a new molecule, or if it reacts with a component of the buffer and forms a new molecule, and if that reaction is not fast on a chromatographic timescale, then you can get 2 peaks. And you can get a whole series of families of peaks that are highly distorted depending upon the rate constant of the reaction, forward and back, relative to the chromatographic time scale. Okay? But acids and bases are so fast, you don't have to worry about the rates of those reactions. They are in equilibrium. So please, don't think you can get multiple peaks out of acids and bases. Okay, so we got to here, micelle formation, and I want to return then to this point in the lecture. And we were talking about various additives that you can put in the mobile phase to induce different kinds of selectivity. Here's an example of another fairly common additive. It's a molecule known as cyclodextrin. There are actually 3 different cyclodextrins. Cyclodextrin is these glucose rings which are connected together to form well, let me show you the picture. To form a cavity, and your solute, if it's of the right size, can go. Your solute can slip down into this cavity, either entirely or partially, and form a pretty strong complex with this cyclodextrin molecule. There are 3 kinds of cyclodextrins: alpha, beta, and gamma, 5, 6, and 7-membered rings. And you choose them depending upon how big your molecule is. But the cyclodextrin, since it's made out of an inherently chiral molecule, namely 5, 6, or 7 glucoses, is inherently a chiral molecule. And so it is capable of differentiating between optical enantiomers. Now, the process of these molecules going in and out of that ring is a rather fast process on a chromatographic timescale. If it were not, this would produce terrible looking peaks. You might even get multiple peaks for your analyte. But as long as this is in excess and it complexes all of your solute, this rate is sufficiently fast that it gives very nice looking chromatographic peaks. This stuff is pretty expensive. So some people, instead of putting it in the mobile phase, they figured out ways of attaching it to the stationary phase. And usually they use these groups here and figure out how to bond them to the basic silica gel or to a polymer. In capillary electrophoresis, what they very cleverly do is they will label one of these groups and put an SO3- on it to give this molecule an electrical charge. Then when another molecule binds to it, the thing has got a charge, and you can separate one compound from another based upon the differences in their electrophoretic mobility of the complex. Since electrophoresis is always done these days in a teeny tiny capillary, it's not very expensive to use this, unlike the situation in LC where you're going to consume quite a bit of this stuff. And so it could get to be prohibitively expensive pretty quickly. I could give literally hundreds of examples of additives that are used, some of which are surfactants, and then the possibility of exceeding the CMC kicks in and all the complexities that adds. But there are many small molecules that don't have the surfactant property that have been used to bring about separations. Any kind of chemistry that you can do that's fast enough chemistry is worth thinking about and maybe even trying. Okay, so we're done with mobile phase issues and we're moving into stationary phase issues. Let me explain this chart. There is a set of about 23 different solutes that we're using here. Each of these data points corresponds to a different solute. And what we're plotting here is we're measuring the K prime of solute X relative to the K prime of benzene on these 4 different stationary phases. the mobile phases were the same for all stationary phases. And so we're taking this ratio and we're dividing it by the same ratio using a C8 stationary phase. So, if I make the numerator a C8 phase and I divide it by the results on a C8 phase, what I'm going to obviously get is an absolutely flat line, and that's this series of points here. And a flat line is, of course, at exactly 1.000, because I'm dividing the same thing by the same thing. Now, if I take a different stationary phase, for instance, if I take a phenyl phase, like that one there, if the phenyl phase were to behave chromatographically, have exactly the same selectivity as the C8 phase, then I'd get another flat line that lies right on top of the C8 line. Okay, so the deviations here indicate a difference in selectivity of the four phases. They cross over here because that's benzene. So they have to cross over there. That's not magic, it's just algebra. So what we're actually seeing here is that a phenyl phase, this guy, is really rather different, both for very polar solutes, which are all down here, and very different for very non-polar solutes, which are way down there. And the high chrome HCC8 phase, even though it's a C8 phase, is very different than the Zorback C8 phase. And the PRP phase, which means a polymer reverse phase, I told you about this the other day. This is styrene cross-linked with divinyl benzene. And there's a lot of divinyl benzene, so it's a very highly cross-linked phase. We can see is not the same as a phenyl phase, and certainly is not the same as a C8 phase. So there are rather differences in retention of these 23, 24 molecules, even though these are all just simple mono and difunctionalized benzenes. They're all completely uncharged. They're neutral molecules. There are no bases, no acids, no zwitterions. They're just chlorobenzene, nitrobenzene, dichlorobenzene, toluene, xylene, cyanobenzene, phenol, benzyl alcohol, stuff like that. Simple molecules. Really significant differences in selectivity with the different stationary phases. This is good because it offers selectivity. So let's look at and compare, using the same set of solutes, different ways we can possibly change the selectivity. So up here in this panel 1, we're using the same stationary phase in both cases, but we're doing 30% acetonitrile on one axis and 50% acetonitrile on the other axis, and we see rather little scatter, right? So changing percent organic modifier, I'm not saying it doesn't affect selectivity, it does, because we have scatter, and the data are much more precise than that. The scatter is due to the fact that we're using two different conditions. And the correlation coefficient is not 1, it's definitely less than 1. So there are some minor effects on selectivity by changing the amount of the organic modifier. Here's another way we can change the organic modifier. What if I use one modifier on one axis and a different modifier on another axis? Well, we get a lot more scatter. Changing the nature of the modifier has a bigger effect, generally speaking, than changing the amount of modifier. Okay? I talked about temperature a little bit. Here's a rather big change in temperature, chromatographic, LC speaking, 50 degrees. You go much above 100 degrees and, you know, you start boiling everything. But of course, you can always put back pressure on it to keep it from boiling. But 50-degree change has a very minor effect on selectivity. Temperature does affect selectivity, but it's even less than changing the percent organic. Here's a change in stationary phase type. This is a silanized silica, and this is a polymer-coated metal oxide. Same solutes. Yes, we get a change in selectivity. It's a little bigger than this, but it's not as big as that. Now this is a totally nonpolar ligand, and this is totally nonpolar. So, you know, it's like two different alkanes. Not a big deal. However, if we compare this polymer-coated zirconia to a carbon-clad zirconia, where elemental carbon, not a hydrocarbon, elemental carbon is deposited by a chemical vapor deposition technique, you see we get a lot of scatter. So sometimes the stationary phase can make a really big difference, as I indicated over here. It depends on what the stationary phases are. Here's more stationary phase changes. And you see, in this case, there's somewhat more of a change than in some of these other cases. Okay. We're going to come back to the stationary phase a little bit, but we have to make a foray into charged analytes. When you have a charged analyte, especially a positively charged analyte, like a protonated amine, and this is by no means a rare situation. Most biological molecules, proteins, peptides, amino acids, nucleic acid bases, it goes on and on and on and on and on, have nitrogens in them, and at chromatographically reasonable pHs, they're protonated. I think 80% of all drugs are amines. It's therefore a very important issue, economically. The problem is, as you know, that when we chemically modify the surface of the silica, we do not get rid of all of the surface silanol groups. Some of them remain as silanol groups, and some of those silanol groups will ionize. The SiOH will deprotonate depending upon the pH. And so what you actually have on the surface is both nonpolar stationary phase groups, the bonded group, and both protonated and deprotonated silanol groups. And the deprotonated silanol groups, of course, have a negative charge. And they can interact with positively charged amines. And since opposite charges attract, there will be extra retention of that amine under these circumstances. It's also true that light charges repel. And so if you had a negatively charged acid at this particular pH, that acid's retention would be less than what it would be if the silanol group were protonated, or if the acid were totally protonated, not ionized at all. And in a situation like this, where we have both a lot of nonpolar functional group, and we have these ionized silanols, we say that the retention is a mixed mode. You have both an ion exchange process going on and a reverse phase process going on. And that very frequently leads to some ugly, ugly peaks. Example, this is a slide from a commercial producer of stationary phases. And they're touting their particular stationary phase with this mixture of uracil, which is a neutral compound, pyridine, which is protonated below pH 6 and is positively charged, and phenol, which is also a neutral compound at pHs below about 10. Now on this stationary phase over here that was made with what we call a high purity silica, a type B silica, which didn't exist at the beginning of HPLC, you get a beautiful chromatogram. But if you use a type A silica, which means a low purity silica, silica that's contaminated, when I say low purity, we're talking subparts per million metal is enough to give you an exceedingly ugly peak for pyridine. It's quite possible that this interaction could be so strong that you won't even see the pyridine come out under these mobile phase conditions. And you have to do something to the mobile phase to make the pyridine come out on certain stationary phases. Here again is stationary phase A and stationary phase B. Let me call it not A and B. Let's call it 1 and 2. This is undoubtedly a highly base deactivated stationary phase where they have encapped the bejesus out of it. And here's a stationary phase which is showing these terrible interactions with those nitrogens. Okay, these drugs are known as tricyclic antidepressants. They differ only in the degree of methylation of that nitrogen. And you can see the peaks are really much, much worse on this stationary phase than on that stationary phase. Okay, what can you do to make life better? Here is a particularly very nasty acting drug, meclizine. It has 2 nitrogens. And so that a pH lower than 3, both of the nitrogens are protonated. So it's a dication, and it's going to really glom onto a negatively charged silanyl group. This is what the chromatogram looks like at pH 1. Meaning there are still some silanyl groups at pH 1 that are not protonated, but if we can lower the pH even further, it's the same stationary phase, the mobile phase, except for the pH is the same. You see that we have a big drop in retention and we get a nice improvement in the peak shape, although this is still far from a really groovy looking peak. But lowering the pH dropped retention, which means some silanyl groups must have gotten protonated. Another thing that you can do to make the peak better is to deliberately add to your mobile phase a compound that will compete with your analyte for occupying the ionized silanyl groups. So here in case A is just a simple phosphate buffer, sodium phosphate buffer, and we get really very ugly peaks. In case B, the pH is the same, but they're using a piperazine phosphate buffer. pyrazine is an aliphatic amine. It has 1 nitrogen. At the pH we're running at 6 here, this nitrogen is protonated. And you can see we get a much nicer chromatogram. And in case C, we're using TMed, which is tetramethyl ammonium ethylene diamine phosphate buffer. Both of these nitrogens are positively charged. They're in the mobile phase. They're going to grab onto any ionized silanol groups like nobody's business. And you can see that the retention here has dropped a lot, and the peak shape is a lot better, although it's still not perfect. I don't know what here are the 3 test solutes that were used in this case. So, lowering the pH to protonate the silanol, adding something to the mobile phase to compete with the charged analyte for the ionized silanol groups are, in addition to improving your end capping and using a high purity silica as the basis of your stationary phase, are ways that you can improve the peak shape. But in the process of improving the peak shape, you are going to affect the absolute retention, and you are going to affect the selectivity. Why do I keep saying that this is due to ionized silanol groups? I think the best experiment I've seen about this is a study where they looked at the retention of lithium ions on 3 different reverse phases. These reverse phases were made in quite different ways. Lithium has no polarity, no non-polarity to speak of. It's, it's a small, teeny tiny ion. It's completely hydrated. It certainly should not like to sit down on a C18 group. And we can see on this stationary phase, these are all 3 Waters products. So the guy who did this study was from Waters. On those 2 phases, you can see even at pH as low as 3, there's definite retention of lithium. And as you raise the pH, more of those silanol groups become ionized, and the retention of the lithium goes up. I can't believe that this is due to hydrophobic interactions. This can only be due to coulombic interactions. The symmetry is definitely better than the resolve, but starting around pH 6, we see this rapid rise in the retention of the lithium, more and more ionized groups. This Xterra was a product that Waters deliberately, and I'm not knocking anybody, and if I don't mention somebody, it doesn't mean I'm knocking them. The Xterra was introduced by Waters for 2 reasons. Number 1, there's very, very little evidence for charge until we get to pretty darn high pH. Maybe pH 9, and we start seeing some charge buildup. That was one reason. And another reason they did it is that this phase is really rather stable in basic solution. These 2 phases here, if they took them up to pH 8, the column wouldn't last a day. The silica underlying the stationary phase would be etched out. It would be dissolved into the alkaline mobile phase. And in fairly short order, you would see the peak shapes for everything become awful. And then you would see a very rapid rise in the back pressure on the column as the particles were rotted away, and then the little particles fit in between the bigger particles and the column would plug up.